So the theme of my talk today is the explicit link between periodic covariance functions and state space models. This is joint work with Simo Särkkä, who is my PhD instructor at Aalto University. The structure of the talk will be that we first go through the basic link between Gaussian processes and state space models, existing work in that sense. Then comes the main topic, that is periodic covariance functions and how to convert those to state space models. This approach is then extended to almost periodic covariance functions. And after that, I discard all the technical details and just try to give you some convincing examples that these methods can truly be used in like real-world settings. Let's start with the Gaussian process regression thing in one dimension. So in machine learning, Gaussian processes are used as flexible priors of functions, where you encode some prior knowledge about the function, how it behaves, typically in time in this case. In Gaussian process regression, the functions itself, they are considered to be realizations of this Gaussian process prior, and then we have some observations y that are observed at discrete time points. And then we can do the inference. In this case, the basic approach scales as On to the third, where n is the number of observations. So, in short, this is a good framework, but computationally quite heavy. All the prior knowledge is encoded in the covariance function, denoted by k here. There's an alternative approach to this problem. It's called the state space approach, where we consider the model to be a stochastic differential equation with some observations of it. In this case, the model is characterized by the model matrices F, that's the feedback matrix, L, the noise effect matrix, and the spectral density QC of a white noise process that is driving the process. Furthermore, we need some observations, and we have an observation model that is in the H matrix. So here, on one side, we have the kernel approach that's used in machine learning, and on the other side, we have a state space approach that's commonly used in signal processing or related fields. These both are quite mature subjects, but basically they're mature on their own, and the links between these are not used that often. The benefit by using state space approach is that it allows us to use very efficient signal processing methods for solving the same inference problem. And this inference problem can be solved in On time complexity. So that's very efficient when n grows large compared to the On to the third complexity. So the link between these two formulations is quite easily understood by considering the spectral density of the covariance function k. That means the Fourier transform of the covariance function. For many model types, if the Fourier transform is of nice form, for example, in this case, this example shows the covariance function of the matter class of covariances and its spectral density. In this case, the spectral density can be approximated by a rational function, and we can solve the same problem by the kernel formulation and the state space formulation. It's exactly the same problem. Here, for example, is some simulated data points, and I have used the same kernel that was shown on the last slide and solved the inference problem. This is using the naive GP regression formulation. This same problem is here solved using the Kalman filtering approach. So it's solved sequentially for each point. making computational scaling scale as ON. This, however, does not look like the solution in the previous slide, but we still have to use some backward smoothing method for getting the full posterior solution. And now you see solutions match. The dashed line is for the naive full GP results, and the shaded patch and the blue mean is from the state space approach. Okay, so this was a quick refresher on how the link between state space models and GP regression problems actually work. Then, the actual topic is periodic covariances. You recall that we had the nice rational function form, the bell curves of both the covariance and spectral density in the previous slides. That enabled us to use like some well-established methods for the conversion. Those methods don't work for periodic covariance functions. I will show you why just in a minute. For simplicity, I will consider only the so-called canonical periodic covariance function here. It can be constructed, for example, like this. We start off with a squared exponential kernel, also known as the Gaussian kernel, or the exponentiated quadratic kernel. We do a change of variables, basically considering x in polar coordinates, and simplified expressions. This is the covariance function in this case. Here on the right, you can see some random draws in polar coordinates from that covariance function, or GP with that covariance function, with different length scales L. So they are periodic. They repeat themselves. The covariance function itself and the spectral density thereof look like this. So the covariance function is truly periodic, and the spectral density is made of some delta peaks. And now it's quite apparent that approximating this spectral density with some rational functions is tricky. It doesn't work. So we have to seek an alternative approach. And this is like the main thing in the paper as well. We consider a Fourier series representation of the covariance. And because the covariance function is symmetric and periodic, it has a very nice formulation in terms of Fourier series. It's an infinite series of cosines with some coefficients qj squared. Now we can think of what sort of differential equation could be used to approximate this sort of models. It's quite apparent that the second order differential equation that gives solutions as sines and cosines is the way to go. So basically we wrap up the polar coordinates into a differential equation. That gives us a state space model where we have the feedback matrix F, the observation model H, and the stationary covariance of state variables P infinity, given in this form. For the canonical periodic covariance function, we can actually solve the qj's in closed form, which gives us something like this. It's given in terms of the modified Bessel functions. There's a very interesting link to the special types of functions here. In the paper, we also show that it's actually when we have an infinite number of these models stacked, we actually get a model that converges to the actual covariance function. But for doing actual computations, we have to truncate it at some degree j. Now, considering only one model, the approximation will look like this. In gray, you see the actual covariance, and in blue, the approximation, both in terms of covariance functions and the spectral density. A two-order model is slightly better. A model of order 3 is quite good already. And with four oscillators, we actually cannot see the difference by the naked eye from the true covariance. So let me reiterate that. So 1 model, 2 models, 3 models, 4 models. Quite good. Okay. In real modeling, it's often desired not to actually have the phenomenon to oscillate exactly, but to allow it to change over time. That's called quasi-periodicity, and that is often constructed as a product of a periodic covariance function and some other covariance function with a very long length scale, allowing the periodic covariance function to decay away from actual periodicity. Here you see a random draw from a quasi-periodic covariance function where you see that the shape of the periodic pattern changes over time. The covariance function and spectral density in this case would look like this. In terms of like the usual GP approach, taking the product of two covariance functions is very straightforward. However, in the state space form, this is not that straightforward. It all comes down to that we need to have the model matrices, basically the feedback matrices, to commute with each other in order to preserve the properties of the quasi-periodicity. Luckily, this can be accomplished by using some special features of the canonical product. I'm going into the details, but the actual state space model for this quasi-periodic covariance model can be given in terms of the so-called canonical sum, the first row for F, and noise effect matrices, the spectral density, the stationary covariance, and the observation model are all given in terms of canonical products. The technical details are in the paper, so now I try to convince you about the actual usability of these methods by showing you some example studies. First, the computational scaling. The naive full GP solution scales as O(n) to the third in terms of number of data points you have. Here, the scale is logarithmic, and it's actually the computational time is shown. The state space solution in this case truly scales as O(n), which enables us to use this for very long time series models in thousands, tens of thousands, even 100,000 or millions of data points. For some actual examples, the first example is considering the Mauna CO2 concentration dataset. Here, I have used weekly observations from the years 1958 to 2000. 2010 for training, and then a couple of years for testing. There are some 2,000 data points, and the model is as follows. I have a very long length scale squared exponential covariance function for the general trend, then a quasi-periodic covariance function for the periodic phenomenon, and then a Mauna 3-2 covariance function for the short scale non-periodic effects. The black line shows, the very thin one, shows the outcome from the full GP, and the shaded patch is from the state space model. So basically, we get the very same result, but with less computational effort. The second real-world example is quite interesting. I like this very much. It's about daily births, meaning deliveries in the US between 68 and 88. It's daily data, some 7,300 data points, and we have a model with a smooth kernel for the the trend, and a bit less smooth trend for the fast non-periodic components. Then we have a quasi-periodic component for the weekly effect and yearly effects. And we can actually model the changes in the periodic effects in birds by using this model. In this case, we used maximum likelihood estimation of the hyperparameters to actually optimize the hyperparameters models. We have six covariance functions altogether, so that we end up with a lot of hyperparameters. And luckily, the Kalman filtering approach lends itself very well to marginal likelihood calculations. It comes out as a side product of the Kalman filtering step. And these same results are also available in the very fresh edition on Bayesian data analysis by Andrew Gelman, where actually this part was written by Aki Vehtari, and this example was actually the motivation for writing the paper on this connection. So, some conclusions. In the paper, we have established the explicit connection between periodic covariance functions and state space models. The thing behind this is that it enables us to use very efficient sequential inference methods to solve GP regression problems in ON time complexity. In the paper, we also showed that this approximate scheme converges uniformly to the closed form solution from the full GP result, and we can also get a rough upper bound for the approximation error. I consider this like a best of both worlds approach. We have a very convenient model specification from machine learning with the very efficient computational methods for signal processing. And combining this is very nice, this frame. There's a poster on this topic. Drop by if you want to discuss this thing with me. All the codes for running the examples I showed you are available on my webpage. And now these methods are also implemented in the GPStuff software package for MATLAB and Octave. Thank you.
Okay, questions?
Nice talk. The Kronecker trick that you showed very briefly, is that correct for any product of two covariance functions, or is it specific to the periodic ones you were showing?
Yeah, that's actually a good question, and it actually is valid for any representation of this type of. If you have the state space formulation, you can construct the product of two covariance functions in this way. It's actually very nice.